Hello there. We have seen the procedure in which we obtain electron diffraction patterns in a transmission electron microscope. We've learned the process of tilting and orienting a crystal in a zone axis. And once you obtain a crystal in a zone axis and obtain a sort of a symmetric diffraction pattern, we learn how to index these diffraction patterns. I will briefly touch a few concepts which I already introduced a few lectures earlier on how the diffraction spots are obtained and what is structure factor. I'll not go in a very elaborate way, but I'll briefly touch upon structure factor again and tell you about how the reflections are coming, that is, how the amplitude of the structure factor is actually reaching a maxima. And then we'll do a very simple exercise based on tilting of the specimen in the transmission electron microscope. Now, I've shown you the example of how the Kikuchi bands are actually used here to act as a guideway or a highway along which you orient your specimen, and you let the Kikuchi node coincide with the bright spot to obtain a symmetric diffraction pattern. Once you get a symmetric diffraction pattern, based on some simple geometric relationships, let us try to index the reflections. Let us try to index the diffraction spots that you get on an electron diffraction pattern. And with the help of this, if you remember the basic structure problem that was defined as a three-level structure problem, where you have to determine the unit cell parameters, you have to determine the symmetry, and then you have to actually determine the position of the atoms. The very first step of determining the unit cell parameters can be done with the help of this simple exercise. So let us look at how we obtain indices in these diffraction patterns and how do you actually get these maxima or extinction of reflections in an electron diffraction pattern. So let me recollect the concept of structure factor. Now let us say here is my equation for the scattered wave. If I say the amplitude of a scattered wave is psi naught with an exponential function of 2 pi k1r plus I f theta times e power 2 pi kr by r. What you have here is by simply superposition of waves by using atoms as scattering centers. If I assume that my atoms are now arranged in a periodic fashion in a crystal structure, we end up with some equation like this. Now, if you see, if here is a collection of my reciprocal lattice points, for simplicity I have taken just a square array of points. If my Ewald sphere is now intersecting with this reciprocal lattice points, wherever I have the intersection, I have the satisfaction of the Bragg's law. Now, based on this, we have something called as the zero order Loy zone, the first order Loy zone, the second order Loy zone, and so on. But now, imagine if this were not a reciprocal lattice but atoms within a real lattice. Let us say I have an electron beam incident on one of these spots at some angle, and it gets scattered through some angle, say theta 1, and then it goes through another scattering phenomenon through another angle of say theta 2, and so on. By the time if I have an incident beam here and I have a resultant scattered beam, I can in principle account for the total effect of scattering through the phase shift that is caused as a consequence of the scattering, and the amplitude I can always get from the principle of superposition of waves by adding up each of these amplitudes, and I end up with an expression like this. If I say capital FHKL is my structure factor, and if the small letters F0, F1, F2 are my atomic scattering factors, I end up with my resultant structure factor as this. Now, if I have a periodic arrangement of atoms, by determining the occupancies of the type of the crystal structure I have, I can see where I get a maxima. This means when I have a periodic arrangement of atoms in a specific fashion, for example, a cube, let us say I have a simple cubic structure, these values of x, y, z in a simple cube have an occupancy of 0, 0, 0, or 111 or 100 and so on. And if I fill in these numbers, I can give the occupancy of simple cube with an equivalent of 000. That means for all possible reflections of HKL, I would get a maxima or a constructive interference. Likewise, this changes when I have the occupancy of a body-centered cubic. For example, if the occupancy becomes 0, 0, 0 and half, 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 I would see that when my sum of HKL becomes an even number, that is when I get a maxima. So this is how the amplitude value changes, and these are essentially called as extinction rules. So if I look at it in more detail, if I now have the expression for the atomic scattering factor as A cell in a more complex summation form given like this, where my net atomic scattering, my net structure factor is given by such an expression. Here are my extinction rules. Like I was just mentioning the previous slide, for a simple cubic structure, for any HKL values, I have my one lattice point, and my extinction rules are such that for all HKL I get a reflection. Whereas for a body-centered cubic, the summation of HKL becomes 2n. Likewise, for a face-centered cubic, I need to have the HKL all odd or even, and then I get the maxima. So based on the type of the crystal class, you actually get different situations where you get a maxima or minima, and you use these rules to actually start indexing the diffraction patterns. Now, what is different between the regular X-ray diffraction patterns and the electron diffraction patterns is, sometimes depending on the orientation of the crystal that you are looking at, not all reflections might actually be visible. As an example, I can take the case of face-centered cubic structure. So let us say I am orienting my face-centered cubic crystal in the 001 zone axis. In this situation, the reflections I see by using the Weiss zone law, there is a possibility that the HKLs for all the values satisfying the condition of all being odd or even should give me a reflection. This means the first set of reflections for all odd or all even for an FCC would be 111, and then I get 200, and then I get 311, so and so on. So now the challenge I have here is, in between I have the 220. So depending on the increasing order of h square plus k square plus l square, the reflections will appear like this. But I was telling about the concept called a forbidden reflection, where when I see the crystal along 001 zone axis, although the reflections of 111 should be present, now because they do not actually satisfy my Weiss zone law, the 111 reflection would not be appearing in this particular orientation. We will look at this in a little more detail when I show you the principle of indexing of diffraction patterns. So moving on, when I have a crystalline sample, I would actually get amplitudes from the unit cell or from the crystal with a varying intensity as a function of the angle of scattering. If I have an amorphous material, I would have some random variations in the intensity, and as I go farther away from the principal axis of the microscope, the intensity eventually dies out. Whereas when I have a crystalline material, the scattered amplitude is always maximum at the direct beam or the central beam, which is along the optic axis of the microscope, and then as I go further away, depending on the scattering angle, these are where my Bragg's angles are being satisfied. The intensity gradually dies out as I go farther and farther. Now, based on these concepts of how these peaks actually appear and what is the structure factor, let us look at how we start indexing the electron diffraction patterns. Now, from these ideas of which reflections would be present on a two-dimensional angular distribution of intensity, if we can use some geometric relation to identify physically when I measure these distances on a diffraction pattern, and if I can relate it through some mathematical relation, I can start making sense of which plane is satisfying this particular reflection or this particular condition where my spot appears, and I can start indexing a diffraction pattern. So, if you look at Bragg's law, I have n lambda as 2d sine theta, and in the transmission electron microscope I have established this earlier already, that the angle of scattering is extremely small. So, you can consider all the beams that are going parallel to my atomic planes, that is, when I orient my crystal along the zone axis, the planes which are parallel to the principal axis or to the optic axis of the microscope, the direction along which the electron beam is propagating, would all satisfy my Bragg's law. Now, based on this, if I look at this schematic, let us say here are my lattice planes with some spacing d. If my incident electron beam is scattered through some angle 2 theta, so if I now look at the effective camera length at which I am recording my diffraction pattern is, say, of a length L, what I have here is a simple geometric relation that tan of 2 theta is the distance that I have here, which is written in capital D over the camera length L. Now, if I use this and the Bragg law together, and assuming the fact that my angle of theta is extremely small, my tan theta now becomes sin theta or more or less theta. So, if I use this in the Bragg law, so I have the d spacing d related through lambda is 2d theta, and if I use this value of theta in this particular expression, so theta is also d over L, which is also equal to lambda over d, I end up with an equation which is of this form, whereas lambda L is dHKL, which is my real lattice spacing, versus capital dHKL, which is my value in the reciprocal lattice. Now, from this, if I have a diffraction pattern on which I can measure this distance capital dHKL in the reciprocal units, that is what you see on the diffraction pattern that is recorded. From a set of diffraction patterns, if I look at an array of diffraction patterns, I know that if this corresponds to a plane H1, K1, L1, and if this corresponds to a plane H2, K2, L2, and let us say this is H3, K3, L3, I can measure these dHKLs from the diffraction pattern, and I know my unit cell value would remain constant from each of these reflections. If I identify what these HKL values are, I can accordingly index from which HKL value these spots start appearing, and that is what we will learn in the upcoming slides. This particular value lambda L, which is a constant for all these ratios that I am trying to determine, is actually called as the camera constant. So, the first exercise that I would like to introduce to you when you start tilting or when you start learning how to tilt a crystalline specimen into the zone axis, I would advise you to actually maintain one of the directions constant and tilt the specimen such that you can determine at least 3 or 4 different orientations from which you get diffraction patterns, and from this you can start determining the unit cell. So, this exercise is not really like a graded assignment, but I will give you as an additional material, I will give you a few diffraction patterns, and I advise you to try this out on your own to understand and see how you can construct the projection of a unit cell from a set of diffraction patterns. So, I will just define the unit cell exercise here. This can act as a tutorial for you to learn how to tilt the specimen and also to learn how to index the specimen, index the diffraction patterns, and also how to determine the unit cells. So let us say if there are 3 sets of diffraction patterns given to you, you first identify the common direction that you have and measure the d-spacings from the reciprocal lattice. This measurement of d-spacings is done based on the methodology that I just told you in the previous slide. Once you have all the 3 patterns with a common tilt axis, so I will show you the examples of this, what I mean by this. What you can do is, you can determine between 2 subsequent diffraction patterns, what is the angle of tilt you physically do to go from one zone axis to another zone axis. For example, I have a unit cell which is like this, and these planes are now along the, if these planes are now parallel to the zone axis now, if I now misorient this crystal by tilting it to another angle like this, so initially these planes which were satisfying and giving me the reflections would have moved to some other direction here, and a new set of planes would actually satisfy my Bragg's law. And when this happens, those planes would also have a new plane normal. So essentially from the difference between this set of planes and the new set of planes which are satisfying my Bragg's law, the angle of tilt that I have to go from, let us say, diffraction pattern set 1 to diffraction pattern set 2 can actually physically be measured from the x tilt and y tilt or alpha tilt and beta tilt I have from the microscope. So once I get these readings, what I can do is I can actually determine the physical angle that your crystal is misoriented or oriented from condition 1 to condition 2 to get the new set of diffraction patterns, and you can determine this by using this kind of a relation. Once you determine these relations, I can start drawing the projections of these reciprocal lattice on a simple graph paper, and I can determine how my unit cell parameters are from 3 different reflections. So if I can determine the angle between the 2 consecutive projections, if I say I have 3 d-spacings measured between these 3 diffraction patterns, and there is one common d-spacing which is common from all the diffraction patterns, then you can actually get a projection of the reciprocal lattice and you can determine what the unit cell parameters are. In the first part of this lecture, I will give you the example of these diffraction patterns. I will show you how you tilt them. The tilting exercise you have already learned in the demonstration sessions, and I will just give you, I will not work out the entire example here, but show you the philosophy of how we get the projection of unit cell, and from this you would have gotten a method on determining the first set of parameters, which are the unit cell parameters which help you solve the crystal structure problem. So we will start with looking at different orientations in which a crystal can be changed within an electron microscope, and what do I mean by maintaining a common zone axis, and then what do I mean by maintaining a common direction, and then let us see how to determine the unit cell parameters. So let us say I have the first set of reflections here from a crystal which is oriented along some zone axis. For now, I do not know what this particular zone axis is. So let me call the zone axis as U1, V1, W1 here, and let us say this particular unit vector I have here is H1, K1, L1, and let me call this as HKL. Okay. I will tell you why I have given this without a subscript of a number right now. So I can actually determine what my zone axis is by applying the Weiss zone law, where I say UVW, HKL and H1, K1, L1 should satisfy such that the determinant of this is 0. So, I can assume some value of UVW to be the zone axis, and depending on which reflections this satisfies for my crystal, I can get some values of H1, K1, L1 and HKL, and iteratively I can arrive at the appropriate zone axis value. But this becomes the part of the next exercise that I will show you. But for now, irrespective of which zone I am in at the moment, please note that I want to determine some random H1, K1, L1 values and HKL values from this particular projection now. So, if I think this is my unit vector, say G1, and if I call this as G, if this unit vector G1 has reciprocal Miller's indices corresponding to values H1, K1, L1, this would have come from a plane which is in the real space with the same indices H1, K1, L1. That is what we established with the reciprocal lattice relation. Now, let us say if this measure of G1, or let us say the value that I determine, if G1 is the vector, if it has a modulus of say value D1 and this has D, this D1 and D together can be used to reconstruct the entire two-dimensional reciprocal lattice that I have in this particular projection. Now, this is, let us say, from the first orientation, which is written as reflection 1 or diffraction pattern 1. Please note that I have actually intentionally given you a crystal with an elongated axis here and a smaller axis here. So, why do I do this? If you look at these reflections here, when we told that the electron diffraction pattern is actually reciprocal lattice, and what you see here is inversely proportional to the real space, this value of these two reflections, the value D that I get from two subsequent reflections, would correspond to actually this sort of a plane which is with a very large D spacing in real space. Likewise, these which are quite farther in the reciprocal space would be coming from some planes which are very closely spaced in real space. So, for example, if I say D1 is from some condition like this and D is from the long axis like this, I should be using my Kikuchi bands which appear like this in my electron diffraction when I converge the beam. I should intentionally maintain this axis constant and go to another node in either this or this or this or this direction, such that this particular set of reflections always remain constant. This comes in very handy when I am actually trying to determine the unit cell parameters from a completely unknown crystal. So, what do I mean by this? Now, from stage 1, getting one diffraction pattern like this, if I tilt the crystal and I get the second diffraction pattern here. So, please note that my D now remains the same, but my D1, let me say, has changed and I get a value D2 here. So, my D1 was slightly larger separation like this, whereas my D2 now becomes slightly smaller, and I use the same principle again. Let us say I get some H2, K2, L2 from this D2. So, this values of D1 and H1, K1, L1 and D I can determine from the lambda L is D kind of a relationship, and from this, for every microscope, based on the acceleration voltage and the length at which you are recording the diffraction pattern, this value would be fixed, and you can physically measure this based on the scale bar you get. So, I have this value also in some angstrom inverse or nanometer inverse, and this is in some angstrom, this is in some millimeter. So, I have all the length values. So, in principle, I should actually be getting my real space D spacings as well. You can use this as one set and you can keep it aside, but once you measure these d spacings and you maintain the tilt axis common, I can go to another tilt axis and now I see that it is moved even closer. So, let us say I get now from this H3, K3 and L3 values. From the set of these 3 diffraction patterns, I have measured D1, D2 and D3 with D remaining common. So, what I can then do is, if I now overlay one pattern over the other, I would in principle get the third reflection which I saw here, the third diffraction pattern which I saw over here like this, and on top of this, this would become the second diffraction pattern which is colored in blue. So, you can see the common axis is overlaid and it remains common with all the others, and the third axis now, the third diffraction pattern now would actually be like this. So, I have the 3 varying D1, D2 and D3 values which are lying here. Now, from this, how do I construct a projection of a unit cell becomes the question. If I say that to go from this reflection to this reflection, I should have misoriented my crystal through an angle, say theta 1, which I can determine from my x, y tilt or alpha beta tilt from the microscope. Also using the inverse sine relationship that has been shared a couple of slides earlier, and then in between this reflection to the third set of reflections that I get from the diffraction pattern here, let us say my angle between these two is now theta 2. I can then measure these individual D1, D2 and D3 values and I can show them as projections on a graph paper. So, how do I do this? I can, based on the angles of tilt, whether these are positive or negative when I get from this relation. So, let me just go back to that relation again here. So, from this particular relation, the angle between the diffraction patterns would either be a positive value or a negative value, and from 3 reflections like this, if I determine one of the intermediate values as the horizontal line by measuring the D1 and D2 values and representing these as theta 1 and theta 2 and marking the distances on a graph paper, I can actually start seeing a projection of a unit cell. So, that is what I will show you in the next slide. So, using the D spacings that you have got from the angles and the angles that you got from the successive diffraction patterns, you can actually do the following. I fix one of the reflections as the horizontal axis, and from this, let us say I tilt through some angle, say I do not know, I can see that this is approximately 26 degrees here among these two, and if I get this from patterns 1 and 2 and I get another set of angles from pattern 2 and 3, and if D1 is from pattern 1, if D2 is from pattern 2 and D3 is from pattern 3, if I now draw the directions here and I look at the smallest repeating unit from this, this becomes my projection of a unit cell. What you can do is to actually get a better accuracy, and please remember that there will always be some experimental errors in orienting the crystal exactly into the zone axis. There is a high likelihood that the spacings you see may not actually be having orthogonal angles between the unit cell projections that you see here, if you are expecting from a kind of an orthogonal Bravais lattice. So, to correct for that, my advice is maintain this common direction which was the closest placed set of reflections which is along this line, and try to get one more diffraction pattern which would potentially be somewhere here or somewhere here. It depends on the angle that you can rotate in the microscope, and having more and more such intermediate reflections and the d-spacings from diffraction patterns from whatever zones or nodes you can achieve through the total tilt range that you get by maintaining a common axis would give you a very accurate determination of the unit cell. So, I will share these diffraction patterns and I will share the camera lens and so on, and please try to construct and see and measure what kind of a unit cell parameter you would get, firstly from the reciprocal values that you get, and then once you convert it to the real space values, check with which sort of a crystal this actually matches. This becomes a very handy tutorial or a very handy hands-on tool to actually learn tilting and understanding diffraction pattern. What you would learn from this is you would actually be very clear in which direction to tilt along which sort of a Kikuchi node. You would get kind of an understanding on which Kikuchi band is appearing narrower, what is the easiest way to tilt and orient the crystal, and while you are tilting, I have told you in the hands-on session, try to tilt or orient the specimen in real space. You can actually see from the channeling contrast that you get from the bright field image that you are seeing from the crystal that it is perhaps close to the zone axis, and this actually becomes very handy. So, with this I would like to stop this particular lecture here, and moving on in the next lecture we will see how to determine the d-spacings and also index the reflections that you get from a specific diffraction pattern, and we will see a few examples and take some examples from the texts on how the diffraction patterns are indexed. Thank you.